Hello, today I'm going to be talking about the signal processing assignment I did. The attempt at extracting information out of a recorded RF signal. So the program used for this assignment is GNU Radio, and as you can see, this is my flow chart, which shows the different signal processing elements I utilized to try to extract this signal. So I'll be explaining them bit by bit. So starting from the left, here we have the file source, which, like I said previously, is the recorded RF signal, out of which we're trying to get out the information. And from the output, we connect it directly to a Qt GUI sync, which basically acts as a spectrum analyzer, in that it shows us the spectrum of the signal that has been recorded. Play it so you have an idea what I mean. Okay, so yeah, if you look at the bottom half, the flowchart at the bottom, you can clearly see this is the recorded signal, and if we using the max hold, we can clearly see the highest points of this signal to find out where there is actually information. Okay, so we notice some peaks here, we notice one here, and the biggest one is here. So we're sure that there is definitely some information right here. So if we close this, I'll explain furthermore. And then the output of that, from the file source, basically we connect it to a multiply block. What the multiply block does basically is it multiplies all its inputs and gives you one single output. That's when you have two inputs, but if you have one input, it basically multiplies it by a constant, which is kind of the case where we need to, that's how we implement the volume of a particular signal. But in this case, we are multiplying it by another signal because we're trying to do what is called frequency shifting. So to do frequency shifting, basically we multiply our signal by another signal in the same phase, another a cosine frequency in the same phase, which is what we've done here. And then the output then goes to this low pass filter. So our low pass filter here has been set to, has a cutoff of 100k. What that basically means is that it's at 100k, every frequency higher than 100k will be attenuated. It's basically only going to allow signals less than 100k to pass through for further processing. So any signals higher than that will be cut off. And here we have the transition width, which basically shows how quickly those signals higher than 100k are attenuated, right? Like, so in an ideal world, naturally it should be I think it should be, this cutoff should happen very quickly, but it never actually happens that fast. So for that reason, it's 500 instead of 0. We've gone with 500 just to account for the fact that we're not in an ideal world, basically. Okay, so after the low pass filter, the signals that come out are then sent into a simple squelch. What this does basically is that it gets rid of background noise. So for instance, the audio that we're expecting, every time there's a silence, there might be some little buzzing sound, basically low power noise. The simple squelch helps to remove those sounds. And as you can see, the setting has been set to minus 20 decibels. So basically those are the low power noises that we're trying to eliminate. And then the signal is then passed through to the WBFM receiver, which is the wideband frequency demodulator. The wideband frequency demodulator, basically. So what that does is that receives this. Okay, so like I was saying, this the WBFM, this is the wideband frequency modulator. This is the receiver component though. So what this does basically is that it demodulates the FM signal so we can recover the audio out of it. And if you notice in this, we have made use of the audio decimation. And oh, sorry, I forgot. In the low pass filter, we have made use of decimation factor of 10. What that does basically is that it reduces the sample rate. It basically divides the sample rate by a factor of 10, such that instead of having 1.2 mega samples per second, which is quite a lot for the signal processing, we're trying to reduce it as much as possible, of course without losing any important information. So by reducing it to 10, it then becomes 120 kilo samples per second, which is what we use and which is what we can see when we run the flow graph. Okay, I'm just going to do that. So we're going to take a look at the flow graph at the output of the low pass filter. Okay, so that will be this one here at the top. So this is basically the new sample rate, the decimated sample rate. That's what we're looking at up here. Okay, and then back to this. So in order to actually get an audio sound out of whatever we're processing, we must try to remember the maximum that a computer speaker can actually, the maximum frequency that a computer speaker can actually produce is 48 kilohertz. So anything higher than that will not, basically you will not be able to hear on the computer. So in this assignment I have gone with 24 because, okay, I'll explain. First of all, from the file that we are processing, the RF signal we are processing, we have a sample rate of 1.2, and we decimated it at the low pass filter by 10 to give us 120 kilohertz. Sorry, to give us 120 samples per second. And then furthermore, we decimated it more at the wideband receiver, basically so that we can reduce it to a level that can be heard on computer speakers, which is what we did. So by reducing it to by 5, what is going to be the output? That's going to be 24 kilohertz, which is the reason why we have gone for 24 kilohertz as our audio sync. And the multiply constant, like I explained earlier, is basically to give us the option of amplifying the signal, and the factor for this amplification can be seen in the variable defined here. So this is the volume variable, where we basically defined a range as well as a step factor, such that we can amplify the signal by in little increments of 0.1, as this case shows us. Okay, so this is my signal, and yeah, that's about it.